let us talk about line integrals. Now we remember that when you talk about integration, you're really adding up elements. And when you get those elements smaller and smaller, you have more and more of them, and the answer gets more accurate. Right? And when the size of the elements approach 0, the number of elements approach infinity, and you use the integration sign. So just a quick revision. Like for the trapezoidal rule, when you look at integration before, it applies to double integration for area, triple integration for volume. Remember the what they call trapezium rule. You have the sum from say A to B, and you want the area. You add the trapezium, the area of the trapezium from A to B. You add them up. So it is a function of x. So you have a function of x here, going all the way up here, a function of x here, goes this height, and so on and so forth. Multiply by, so it's height times width. And the width of each trapezium, you remember, was delta x, right? So that's what the width of each trapezium. So this is the height, f of x, what we call y, times the width delta x. But then you make the trapezium smaller and smaller. And the smaller you make them, the more of them you have to add, but the more accurate the answer becomes. And when the width gets so small, they approach 0. The limit as delta x tends to 0 would be, you change the summation sign to the integral sign from A to B of f of x, and then you change the delta x to dx, right? So with integration, you're summing up a number of small pieces, and as those pieces get smaller and smaller, they are approaching 0. The number of them get larger and larger, approaching infinity and infinite, the large number of them. So that's integration. Now that applied to area integration, that's double integration, or in this case, remember this was really double integration, but we bypassed the first part of it. You remember that in the double integration class. But now let's look at what they call line integrals. Alright? So suppose you have this curve. This curve is y equal f of x, some function of x, whatever it is, right? It could be some path that you're moving some object along. And so you're going from here, which we call A, and from here, which we call B. Alright? Now, as we go along, we move the object along the curve. And it could be, for example, you are pushing an object along this curve with a force, right? And it moves covering a certain distance. You know that work? Equal force times distance, right? Now, here, when you reach here at this point, call this K, right? You have the direction of movement at this point right here is going to be a tangent. This is a tangent. Okay? Remember, the direction keeps changing because it's a curve, it's bent. But this is a tangent. Now, Let's call this FT, the tangent, the tangent force. Now, the thing is, you can have this force moving, say, at a particular point from, let me see now, from this point to this point. All right, I had called this K. It has moved past K and is now right here. Now the length from K to L, let's call it delta S, where S is the length of this arc, right? S equal arc length. So it's the length from K to L, right? Now, the work done when you move from K to L is equal to the force, the tangent force multiplied by the distance that you move, which is delta S. Let me rewrite the S part. You see that? Force times distance. So, here now, if you should keep doing this, you break this up into various parts and you add them up. You want to find the work done, total work done. From A to B, as you move from A to B, what is the total work that is done? Well, it would be the sum of Ft times delta S. Because you have an Ft times delta S here, you have an Ft times delta S here, another one here, another one here. Alright? You keep adding them up. But then, if you do that, you get a certain answer. But this line does not really follow the curve directly. The answer wouldn't be accurate. It wouldn't be perfectly accurate. Right? Because if you go from here to here, it would be along a straight line. Right? And if you have the curve like this, a straight line would be more like this. So it would be a bit shorter than the curve. So it wouldn't be perfectly accurate. So now, suppose you, instead of having 1, 2, 3, 4 parts, you break up into 1, 2, 3, 4, 5, 6, 7, 8 smaller parts now. So you have a tangent here, a tangent here, 3, 4, 5, 6, 7, 8. So here you have smaller, what do you call, arcs, but you have more of them. You would have a more accurate answer. The smaller you break up the line and calculate the work, add the order of the work, the more lines you have to use, but the more accurate the answer becomes. Right? Now, if you break up the line into arcs that are smaller and smaller, or, well, it wouldn't be arc, it would be more like chords, right? I should say chord, because the line that touches 2 points on the circumference is a chord. The arc would be the bend, right? So I should say chord. If you break this curve, divide up this curve into many more cards and add them up, those would be the distance. The force times the distance, it gets more accurate. And then the limit as delta S tends to 0. The length of the card tends to 0. Instead of having now the summation sign from A to B, then what you have, let me repeat the summation below here. Let me just erase this. So the summation sign from A to B, from A to B of f of s or f of t, yeah, the tangent f of t times delta s. Remember, this is the length of the card, and this is the force, tangent force, work force times distance. Now the limit as delta x of this tend to 0 would be equal to what? Let me erase this thing. You change this to integral from a to b of f of t dx or ds. I put x there instead of s. It's ds. From what I remember, I'd use s for the length of the card. Right, it's delta s. So I put x for, it's s. The length of the card, s. Right, see it here? So work is force, the tangent force that you're pushing the object times the distance you move. You're changing the length of the card, delta s. So if you break up the card into more than one, if you break up the curve into more than one cards, you're summing up the force, the total work from A to B of the tangent force here times the length of each card, but but if you make the card smaller and smaller, you have more and more of them to add up. And as the length of the card approach infinity, the number of cards that you have to add up approach. The length of the card approach 0. The number of cards you have to add up approaches infinity. So what you have is the sum of that, the integral from A to B of the tangent force times the s, the length of the card. Alright? So that's what you have there. But the thing is, since it is an integration along a curve AB, the way it is written is like this. Instead of putting AB, A at the bottom and B at the top, it is written like this. Right? Showing AB. But if you already know that the curve is from A to B, and you're doing, you already are aware of where A starts and where B starts. You don't have to put A, B at the bottom of the integral sign. This is the same thing as this. You just put C to show that it's along a curve of f of t ds. Alright? So that's the way it is written. Right? That's the way it is written. So here, you know that C is equal to a curve from A, which has coordinates x1, y1, to B, which has coordinates x2, y2. Alright? So the integral, line integral, is about integrating is about integrating along a curve. And remember, when they say curve, it could very well be a straight line, and they call it curve, right? But when they talk about integrating, cutting up a line or a curve into parts and adding them up and making each part's portion get smaller and smaller, that's what they call a line integral. And the way you show the integral occurring along a curve is this. Alright? Alright, so we'll continue talking about it in our next video. So I'll see you.